In the last video, we analyzed the response of an electromagnetic wave to a vacuum. More specifically, we looked at the intrinsic impedance and the complex propagation constant of a wave as it travels through a material that we called a vacuum, in which there was no charge and the conductivity of the material was zero. Well, what about the types of materials we find on Earth? Earth, we don't have vacuums here very often. Most electromagnetic waves are traveling through air or in a transmission line or something like that. And we broadly, when we're talking about materials, we're broadly talking about two classes of materials. One's a dielectric material and one is a conductor. And you guys are intimately familiar with these as electrical engineers. You're very used to dielectrics as insulators and conductors as, the conductive elements in your circuits. Well, what makes a material a dielectric? What makes a material a conductor? And it turns out that this is really the response of the material to the electromagnetic wave propagation, and in particular, it has to do with the intrinsic impedance of the material and the complex propagation constant of the material. So let's just start analyzing dielectrics and conductors by, again, defining what intrinsic impedance is. We calculate it by saying it's j omega mu divided by sigma plus j omega epsilon. So we see it's got a frequency content, it's got a material property content, frequency content, material property content, right? And remember, that's just the relationship between E bar plus and H bar plus. And in general, we say it's just the relationship between the electric field magnitude and the magnetic field magnitude. I know that looks like an A down there, that's an H, right? The second property that we're interested in is the complex propagation constant, and that's equal to those same terms just multiplied together, j omega mu times sigma plus j omega epsilon. And this is equal to alpha plus j beta, where this tells us attenuation, and this tells us wave number. And so this this is telling us the relationship between the E and the H fields in the plane wave, and then this is telling us how much does that plane wave attenuate in a material, and what is the relationship between propagation velocity and angular frequency. It's basically what wave number is telling us there. So how does this relate to dielectrics and conductors? Well, we see the term here that we can kind of manipulate is that there is in the denominator here and in part of the multiplication here, we've got this sigma plus j omega term. And what we can do is we can say, okay, well, in some materials, sigma is going to be really, really large. That's how, sigma is how well it conducts electricity. So sigma might be really, really big in a conductor, or sigma might be really, really small in an insulator. Alternatively, we could just say that this term gets really, really small at low frequency, or it gets really, really big at high frequency. So we can control two different properties to say, well, this part of the denominator matters more, or this part of the denominator matters more in the mathematical sense. And so the first situation we're going to look at is when the omega times epsilon product, so omega epsilon, is much, much larger than sigma. And this can either be because frequency is high or because sigma is particularly low. And I'm just going to move over here. And in this case, eta, the intrinsic impedance, is just going to simplify down to mu over epsilon. And we see that the intrinsic impedance, the relationship between E and H, is purely real. Right? There's no J term in here. And there's no phase shift. There's no angle or anything like that. Complex propagation constant, if this goes to 0, is going to be j omega mu epsilon. Sorry, root mu epsilon. Which is just equal to j beta. And we see that therefore alpha is equal to 0. So there's no attenuation. And so if mu and epsilon are in phase with one another and there's no attenuation, we call that a dielectric. Well, what about the case where omega epsilon is much, much less than sigma? Oh, sorry, that looks like a 0 there. That's supposed to be a sigma. Well, in this situation, eta is equal to j omega mu divided by sigma root. And what we can do here is we can pull out the square root of j out front, and we're left with omega mu over sigma. And so this is equal to square root of omega mu over sigma at an angle of pi over 4. And then gamma, we see that's just going to be j omega mu sigma root. And if we were to combine this into its real imaginary parts, we'd find that alpha is equal to beta in this case, which is equal to omega mu sigma over 2. And these results show us that for, in this case, the E field leads the H field by pi over 4 radians or 45 degrees. The intrinsic impedance also increases with frequency, and both the attenuation constant and the phase constant are going to increase with frequency. And we call these are the properties of materials that we typically call conductors. And we've developed a simple way to determine whether a material is a dielectric or a conductor at a certain frequency, and we call that loss tangent. And what loss tangent does is it just numerically compares the omega epsilon product to sigma. And we do that by drawing a little triangle. Call that angle theta. The opposite side of the angle is the conductivity of the material, and the adjacent side of the triangle is the product of angular frequency and electric permittivity. And so from the definition of tangent, tangent of theta is equal to sigma divided by omega epsilon in this. And if we have a tan theta that is less than about 0.01, we'll typically call this a dielectric material. And if tangent of theta is greater than or equal to about 100, we call this a conductor. In between these two, the material is often called a quasi-conductor. So I've done some calculations here to just, there's a couple mistakes here. This is not inverse tangent. Anyway, I've done a couple calculations here to illustrate frequency dependence of whether a material is a conductor or an insulator. And what we have here is dirt. Dirt, if you measure it, it's going to vary based on where you get the dirt and how wet it is and stuff like that. But dry dirt's going to have a relatively small conductivity, 0.008 milliohms per meter, and a relative permittivity of about 12. And we just want to determine the conductive nature of dirt as a function of frequency. And so to do that, what we need to do is calculate the loss tangent. So the tan theta is just sigma divided by omega epsilon. So what I've done here in all three of these equations is I've put in sigma, which is just 0.008, the conductivity. In the denominator, I've got omega, which is 2 pi f, so 2 pi times 100 kilohertz, 2 pi times 10 to the e to the 6 megahertz, 2 pi times 10 gigahertz down here. And then what you need to do is put divide by the relative permittivity times the permittivity of free space, so that's 8.854 times 10 to the minus 12 times 12, so all those go in the denominator. You do those calculations. So at 100 kilohertz, you find out that dirt has a loss tangent of 120. Notice there's no units. Since tan theta is greater than 100, we call dirt a conductor. At 100 kilohertz, dirt's a conductor. At 10 megahertz, we see that the loss tangent changes to 1.2, and so therefore dirt is a quasi-conductor at 10 megahertz. And then increasing frequency to 10 gigahertz, we see that the loss tangent of dirt at 10 gigahertz is 0.0012. Loss tangent is therefore it's significantly less than 1, and we will call dirt at 10 gigahertz, we will call it an insulator. So this example is showing us that what we consider an insulator or conductor is actually frequency dependent.